Hey, good morning, everybody. This is Mr. Aynesworth, and we're going to get into section 9 here in financial algebra. We're going to be talking about how to optimize a business situation here. We're going to be talking about linear programming, systems of inequalities, and we're going to be talking about something that George Dantzig, the guy that you're looking at right here in the upper left, invented back in the between 1945 and 1955. All right, to optimize a business situation. All right, and so basically what we're going to do, if you look at the objectives up top, is we're going to formulate or learn how to formulate a linear programming problem given a real business context here. We're going to learn what a feasible region is, what corner points are and what they're used for, and basically use everything you learned in Algebra 1 with systems of linear inequalities to solve a business situation. Okay. Now this was developed back in between 1945 and 55 by actually 3 people. All right, George Dantzig was one of 3 guys that really rose in math during that time in respect to American mathematics, and it was basically solve industry and economic planning problems. Okay, and so what we're going to do is we're going to go through the prerequisite skills that are necessary to solve such problems, and we're going to go back and actually revisit what you learned back in Algebra 1 in terms of linear inequality systems. And we're going to just step it out and go through the basics. So this first part here is not a full linear programming problem that you're going to see in your workbook. It's the basic skills needed to actually be able to do that. And we're going to have Desmos off to the side. We're going to back up everything we do with Desmos and verify everything we do. So open up your Desmos account right now and title it like I did right here. And notice that I said 9.9 Optimal Solutions Linear Programming. Go ahead and get that set up and so that you can verify what we do by hand with Desmos, which is kind of nice. All right, so let's go ahead and take a look at it here. What we're going to do in the very first part, when you learn what a linear programming problem is graph what's called a feasible region. Okay, now feasible regions are simply the solutions of a system of inequalities, which, as I said earlier, you did back in Algebra 1, but it's probably been a long time. So we're going to go through all the basics here. So feasible regions are the location. It's actually a bounded region that represent all the feasible meaning viable, possible, correct solutions to a given set of inequalities. And in reality, these are the inequalities which are called constraints or limitations to a linear programming problem. All right. We're going to use the corner point principle that George Dantzig actually proved, and it basically states that the optimal or best solution that either minimizes or maximizes the objective function, which we'll talk about later, always occurs at one of the corner points. So in this first set of examples here, which are really, really basic, we're going to graph and go over the basic skills of graphing a linear system, which is it's just basically 2 or more linear inequalities. And we're going to bound that region, find the corner points, and just state them. And later on in part 2, we are going to actually apply the corner points and actually solve a real problem. But we're going to go over just the basics first. All right, so we're going to do it all by hand. So let's take a look at number 1 here and go back in time and just review how to graph a system of linear inequalities. Okay, all right, so the first one here, we need to graph the system, and the system has 3 linear inequalities here. And we're going to graph it one by one. Okay, and then we're going to, highlight the region over here. I would also get out some colors here. I'm going to do mine in color. If you have colors, that'd be great. If not, just get out a highlighter at least so you can highlight the feasible region, which is the end result, the most important part of it here, so that we can locate the vertices, or called corner points, of what's called the feasible region. Okay, this is a vocabulary coming from George Dantzig, like I was saying earlier. Okay, so number 1 here, we have to graph x greater than or equal to 1. So if you look at the x-axis here, the x-axis, well, let me put this in color here, so this is number 1. All right, you see 1 here, all x values that are greater than 1, greater than or equal to 1, excuse me. All right, obviously start at 1 and go to the right. Okay, so this has a vertical boundary line right here. All the x values that are greater than or equal to 1 lie to the right of this vertical line. Okay, so here we go. Here's your first linear inequality. So I'm going to label that x greater than or equal to 1, and I'm going to show where those x values are located using arrows. Now, when we do a Desmos, they're going to show shaded regions. Okay, so but we're going to use the arrow technique. So linear inequality number 1 here is that we're going to, when you want to graph all points who have x coordinates greater than or equal to 1, it has to be to the right of this vertical line. All right, obviously to the left is values less than 1. We want all values greater than or equal to 1, so they must lie to the right. Now, as I was saying earlier, we're going to verify everything with Desmos. Okay, so we're going to go over here, and again, have your computer split screen here so you can use Desmos as I'm doing here. So just don't copy and take notes. Actually, type these equations in your Desmos here and pause and play through the video. All right, that way you have a full experience, because if you just watch me, I'm getting good. Okay, if you do it with me, then you're getting good too and you're learning. So type in x greater than or equal to 1, and you'll notice that it's a shaded region to the right of this vertical line passing through 1 on the x-axis. Okay, so there you go then. Pretty simple. Okay, so what I just did there on the left on my paper here is verified by Desmos. All right, next one right here, we want to graph, and I'm going to switch colors here, y less than or equal to 8. So you want to figure out on the y-axis where 8 is, okay? So you locate 8, and you want to graph all y values that are less than or equal to 8, and they have to lie below this horizontal line right here. And obviously, if the y value is less than or equal to 8, then it's below this horizontal boundary line. All the values that are above 8, okay, lie above this line, but we want all values, y values that is, that are less than or equal to 8. And so it has to be a horizontal line passing through 8, all right, and below. So notice that my arrows are shading below. Okay, so this is horizontal. The previous one was a vertical boundary line. Now the second one, y less than or equal to 8, is a horizontal one. And so we go to Desmos here, and you just type it in, y less than or equal to 8. All right, and notice that if you just look at one at a time, notice that it's a horizontal boundary line passing through 8 on the y-axis here, and notice that it's shading down. All right, let me see if I can change the colors here. There we go. And then my first one here. Let me turn this one on. This one's blue. Get everything color coded, huh? Oh, this is slick. Okay. Okay, so there we go. All right, now it corresponds to my own work here. Okay, the next one here, what we want to do is we want to graph this third inequality right here, and number 3, and then we have y minus x is greater than or equal to 1. Well, you get it in slope-intercept form, and the slope-intercept form looks like this: y greater than or equal to mx plus b. So typically, people, you isolate the y variable, and then you understand the slope and the y-intercept. So we're going to go back and just do what we did back in the day in Algebra 1. Okay, so here we go. We're going to add x here, and so y is greater than or equal to x plus 1. Just add x to both sides. And notice that the slope right here, 1, the slope is 1, which as rise over run is 1 over 1. So it's up 1, right 1. Remember, it's rise divided by run. And the y-intercept is 1 here. B is 1, so b equals 1. That's called a y-intercept. Okay, so what we do is we start plotting. And, I'm going to do this one in red so it kind of pops out. So I'm going to switch colors here. So the third one's going to be in red. I'm going to start at 1 here on the y-axis. And then I'm going to go up 1, right 1. Up 1, right 1. Up 1, right 1. Up 1, right 1. And just keep on going here. All right, y, and then you just keep on plotting a bunch of points. Take out your ruler, and then draw your line, right? Now it's greater than or equal to, so these are all solid boundary lines. If it was strictly greater than or less than, they would be dotted. Okay? Now it's greater than or equal to, so we want all y values that are greater than or equal to x plus 1, And so if you take a look at the inequality right here, and make a little note, all right, you shade above boundary line. Okay, BL is boundary line. Okay, so I'm going to indicate that by the upward arrows here. So this is y greater than or equal to x plus 1, and that's inequality 3. Okay, so the question is where is the feasible region? Where's the bounded region? So before I do that, let's just turn off these colors and let's enter the equation in here first. You can type in y minus x greater than or equal to 1. You can type in the original inequality and notice that it's shaded up here, just like I did. Or you can type in the end result. After isolating y, you can type in y greater than or equal to x plus 1. It's the same thing. So notice that if you turn off the previous one, you get the same equation right here, or the same shaded region. It really doesn't matter whether you enter the original inequality or the one that's has y isolated. It doesn't matter. Okay, but I'm just gonna highlight this one because I want to keep everything color coded. Now you want to figure out where the feasible region is, and the feasible region, right, is where they all intersect. Okay, so let's write that down. Highlight the feasible region where they all overlap. Okay, where they all overlap. Overlap, or you can say intersect. That is a solution. That's the solution to any system. It's the intersection. So where does the blue and the green and the red overlap? Okay, it's where the arrows, all these colors, the blue, the green, and the red, where they all overlap. And in Desmos here, if you turn on all of them, it's the darkest region right here in this triangular region right through here. So I'm going to shade it in here. So get out your highlighter here, and let's shade in this triangular region. This is where all three colors overlap. This is what's called the feasible region. This is the solution to the linear system. So let's write that out. So this yellow region here is called the feasible region, and it's simply where they all overlap. Okay, and that is on Desmos here. It's let me just plot these points right here. These are the corner points. These are the points that we're interested in right through here. This is where they all overlap. So let me grab this in so I can bring this in. There we go. Let me decrease that. There we go. So let me highlight the corner points of the feasible region here, which are these three vertices right here. And let me bring this into the lesson. Okay, so what you see off to the right here in color is from Desmos, but it corresponds to everything I'm doing here on paper. Okay, so this, let me highlight it here. So this region right through here that I'm highlighting is what's called the feasible region. Feasible region. Basically, it's the solution region, okay? Feasible region. Okay, all the solutions are in here. It's called the fancy name is feasible region, but it's basically the solution region. And we have three corner points because it's a triangle, and we have a corner point at A, and then one at B, and then one at C right here. So one at A here, one at B here, and one at C here. These happen to be the solutions to the linear programming problem that we're going to be solving in our main lesson, which is going to be coming up in part 2. All right, right now we're just going over the basic skills, the nuts and bolts of how to do this, and then I'll discuss how to solve a real problem later on. So it says write down the vertices of the region. Well, the first one is 1, 8. All right, the second one at B is at 7, 8. All right, and then the third one, C, that is at 1, 2. Okay, the way you label them, A, B, and C, doesn't matter. The only thing that matters is are the coordinates. Okay, I just use A, B, and C just so I can, I'm an instructor, so so we can talk about them. Okay, so we have 3 corner points or 3 possible solutions. The question is which one optimizes a linear programming problem that either maximizes or minimizes either the profit or the cost of the problem, depending on what the problem is. And you're going to see that again in part 2. Right now we're just building up the basic skills. All right, now remember, this feasible region is where they all overlap. So this first inequality here, y less than or equal to 8, that's going down. The second equality, y greater than or equal to x plus 1, that was going up. All right, and then the third one here in blue, x greater than or equal to 1, that's to the right. All right, not to the left, but to the right. And so wherever they all overlap is the feasible region. In this case, it's the shape of a triangle, but it doesn't have to be. It can be any polygon whatsoever. It can be multi-sided. It depends on how many vertices, or excuse me, inequalities there are. Okay, and that's just one little example right there. So let's get into another one here so we can get a little bit more experience. I'm going to just go over 2, and then you guys can do the rest 3 and 4, and I'll check those in class. All right, but one example is never enough, so let's go through it one more time. All right, so what we want to do first is we want to graph the first inequality here, x greater than or equal to 3. So you find 3 on the x-axis, okay? All the x values that are greater than or equal to 3 lie to the right of that, okay? So you're going to shade to the right. And what I suggest you guys do is draw a bunch of arrows, because the feasible region is where they all overlap. And then I also suggest that you write down the inequality next to your boundary line, okay? To show which is which. All right, next one, x greater less than or equal to 7. So I'm going to switch colors every time I do this, so you find 7 on the x-axis. All right, and all x values that are less than or equal to 7 lie to the left. Okay, so x less than or equal to 7. Obviously, they have to be to the left of the line, not to the right, because like 6 is less than or equal to 7, right? So you have to go to the left. Oh, and I forgot to do a little Desmos action here, so let me do that. Okay, so I'm going to turn off these colors here, and then click on save. Make sure you save all your work. All right, let's enter in the next system. All right, so x greater than or equal to 3. Okay, so you can see that is to the right, as I indicated in light blue, or the turquoise. And then the next one here, x less than or equal to 7, so type in x less than or equal to 7. And notice, let me turn off the first one here, notice it's to the left of 7. Okay, so you can see that more clearly. All right, so you can check your work as you go here. All right, and then the next one here, y is less than or equal to 10. So I'm going to put this one in purple. So y, you find 10 on the y-axis, all right, and you draw a horizontal line, and all y values that are less than or equal to 10 are obviously below it. Okay, y less than or equal to 10. Notice that I'm labeling everything as I go, and then you type that in Desmos, so y less than or equal to 10. Okay, and you turn off the other colors so you can see one at a time. And notice that it's shaded below 10 because all y values that are less than or equal to 10 are below that line, not above but below. Okay, and then the last one here, we've got y, okay, we got x plus y greater than or equal to 8. If I subtract x, I get y greater than or equal to negative x plus 8. So your slope is negative 1, and your y-intercept is 8. Okay, so you start at 8. Now I'm going to, let me see, I've got to pick a different color here. So I'm going to do this one here in orange. So I'm going to start at 8, and I'm going to go down one, right one, down one, right one. Okay. Now the inequality is greater than or equal to, so if you look right here, you got to shade above. Okay, greater than or equal to is always shaded above. Okay, so you draw your boundary line, okay, and you shade above, and you draw a bunch of arrows, okay, and this is y greater than or equal to negative x plus 8. Okay, so the question is where do they all overlap? Where does the orange, the blue, the green, and the purple overlap? Okay, and so you, first of all, you type this in Desmos here. So you can type in the original inequality, doesn't matter. So y, x plus y is greater than or equal to 8. Okay, and then the darkest region here will be, see, it's kind of hard to tell where they all overlap. But on my paper here, because I got arrows and colors here, it's easy to see. So it's where they all overlap. And it's in this trapezoidal region right here. Okay, so highlight this, and we've got 4 corner points because it's a 4-sided figure. Okay, so let me highlight the corner points. We got one at A, one at B, one at C, and then one at D. So we have 4 corner points. A, B, C, and D. So A, it looks like 3, 10. If you just look at the graph, B is at 7, 10. Notice that I don't need to figure this out using Desmos. Okay, I just look at the graph. C is at 7, 1, and then D is at 3, 5. Now, what we do is once we do this, then we go to Desmos and then we click on them. Okay. What's cool about Desmos is you just click on your corner points and they show up. Okay, and you'll notice that the 4 corner points here correspond to the 4 corner points on the left. All right, so let me grab this here just to show you. There we go. All right, so we have this feasible region in red right here. So all of this is your feasible region right here. And this is A, and this is B, C, and D. And then of course, later on we're going to just put all these skills in and solve a full-on linear programming problem where you guys learn how to maximize or minimize a business situation. All right, because we're in financial algebra, right? And so we need to actually apply it to a business situation because that's what you guys are here for. All right, learning how to do it in a financial situation, okay, which is a business situation. All right, and then so those are the basics. It doesn't get more complicated than that for linear programming because it's linear, right? And they're all in proper, linear form, y equals mx plus b. All right, now what I want you to do now is to try these two, okay? You got system 3 here. Go for it. Make sure you verify it with Desmos when you're done, and then try system 4, and then go ahead and submit that in Canvas when you're done, and then we'll get into part 2 when I see you guys next. Okay? All right. Well, this is Mr. Aynesworth here. This is just a little short little video just to get you guys prepped and ready to go with the basic skills that are necessary for linear programming. I'll see you next in the next lesson here. All right. Take care. Work hard. Finish your work and submit it in Canvas, and I'll see you later. Bye-bye.